Good afternoon. It's my pleasure to be here again for my course, Engineering Thermodynamics. This course is for the third semester Aeronautical Engineering student as well as the mechanical student. I am in the last class of my module 4 lecture. In this lecture, I will be discussing about Bell Coleman cycle efficiency. Before this, I have already covered the basic concept of Bell Coleman cycle, its application in aircraft refrigeration and air conditioning system. Before that, I have already taken 4 important cycles like Otto cycle, diesel cycle, dual cycle and Brayton cycle. In this system, the Bell Coleman cycle is opposite or reverse of the Bell Coleman cycle. So, if you see the cycle, till now all the cycles were in the clockwise direction, starting from 1, 2, 3, 4, 5 like this. But this will start from 1 to 2, 2 to 3, 3 to 4, 4 to 5. It is in the anti-clockwise direction. Bell Coleman cycle is a reverse of Brayton cycle. Brayton cycles are used for gas turbine engines. Nowadays, most power plant aircraft aero engines like turbojet engine, turboprop, turboshaft, ship's engine, they all are operated on the Brayton cycle engine. The Brayton cycle engine is also called as Joule engine, Joule cycle. In Brayton cycle, we have seen that initially one compression was taking place from 1 to 2. It is isentropic compression. From 2, the fuel was injected, heat was added at a constant pressure, 2, 3. From 3, after burning of the fuel, the pressure and the temperature was increased tremendously. This high temperature gases are entering into the turbine. In turbine, expansion of the gases are taking place. All of a sudden, the temperature is reduced tremendously. So here, if you see that, the effect of the turbine is to reduce the temperature and hence they produce the work. But the same principle will be used in our Bell Coleman cycle, where the turbine is, the main objective of turbine is not to produce the work, but to produce the cooling effect. Because the main purpose of the turbine is to produce work by reducing the temperature. Or if you give the work, it will reduce the temperature. So here, same principle we are using in a different way or in the reverse way. So we can say that the Bell Coleman cycle is a reverse Brayton cycle. So I will be discussing in this lecture about Bell Coleman cycle efficiency. So in my previous lecture, so today we will be talking about Bell Coleman cycle efficiency, and one numerical we are going to undertake, and we will see that how we are going to solve this problem. In the previous class, I have covered the introduction to Bell Coleman cycle, and we have seen that the Bell Coleman cycle, if I see it is a PV diagram. So initially it will start from point 1, a isentropic compression. From 2 to 3, it is isobaric, S is equal to C, and it is a compression. 2 to 3, it is a P is a constant. It is called isobaric. From 3 to, again it is 3 to 4. This is the isentropic expansion. It is an isentropic compression. It is isentropic heat addition. and here it is isobaric heat rejection. These are the four processes which the Brayton cycle is having. Brayton. So now introduction to Bell Coleman. So in this Bell Coleman cycle we have already done the process, and in that we have seen that how the cooling effect is produced. Bell Coleman cycle diagram. So Bell Coleman is opposite to this. So if I remove this arrowhead from here and change the number, then it will become the Bell Coleman cycle. Construction we have seen, PVTS diagram we have seen, working of Bell Coleman cycle we have done, process in the Bell Coleman cycle, aircraft refrigeration we have done already, I think you remember, COP, derivation of aircraft refrigeration system. This we have already done. Now I will discuss again for the Bell Coleman cycle. Here if you see, starting from the point 1, here is a refrigerator. Here we put the vegetables, all eatable items. Assume this is the room also. If you want to make room, or you can here put some cooling items here. So from here, the compressor, every refrigerator will have one compressor. The object of the here we will have one motor. This is the motor. So this motor is operated by electric power. Some part of the work is obtained from the expander, but 70 to 80% of the power is obtained through the external source, that is the electric motor. So it is rotated. By the rotation of this compressor, the air which is sucked from this refrigerator zone is very low temperature and the low pressure, and it is entering in the combustion in the compressor, and in the compressor, due to its reduction in the volume, the pressure and the temperature is increased. Pressure is increased and temperature is also increased. So from P1 to P2, if you see the P2, this P2 is greater than P1 and T2 is greater than T1. So that is the objective of this, but V2 is less than V1. So this V1 will be less, V1 will be more, V2 is less. Now this high temperature and the high pressure. So here if you see 1 and 2, this 1 and 2 is the process which is the isentropic compression. And now this 2 to 3 is cooling, and it is a constant pressure isobaric. Isobaric cooling is done. Then 3 to 4 is expansion, isentropic expansion, and now 4 to 1 is heat rejection. 4 to 1 is heat rejection at the inlet of the compressor. So if you see this 1 and 2, here 1 and 2, here pressure is increasing, here temperature is increasing. 2 to 3, here pressure is constant but temperature is reducing. The cooler is reducing the temperature. Now 3 to 4, it is expansion is taking place. Further temperature is sharply falling down from 3 to 4. Pressure is also falling down sharply and the expander. So you reach to the 4. From here, it is a cooling box. Here it is passing from here, and due to this passing from here, it is extracting the heat of this object which are kept here, and the pressure and the temperature is increased, but pressure will remain the constant. So here we have the 4 processes in Bell Coleman cycle. Process 1, isentropic compression. Process 1 and 2, isentropic compression. Process 2 and 3, isobaric heat rejection. process 3 and 4 is isentropic expansion. Process 4-1 is isobaric heat absorption. So here 4-1 it is absorption. Absorption means heat is absorbed from the place where we want to do the cooling effect. So here this PES and TS diagrams are shown and they are taken from the reference 2. Now we have to calculate the efficiency of this cycle as we have done in each previous cycle, but here the process is little reverse. So we will see here that how we are able to do this. We are able to calculate the efficiency of this Bell Coleman cycle. So here process 1-2 is a isentropic compression. So we will take the process 1 and 2. So here temperature is T2. So just I am writing here temperature T2. Here is temperature T1. Here is P2 is equal to P3 and here is equal to P1 is equal to P4. And these are the S is equal to constant and here S is equal to constant, P is a constant and here also P is a constant. This is the compression and this is the expansion. This is the cooling and this is absorption. Okay, so taking the process of the compression, that is 1-2 isentropic compression. So here work done on the compression and this work done is done by the help of some external source like electric motor and some part of this thing is obtained from the expander also. So MCP T2 minus T1. MCP T2 minus T1. Now if you see the isentropic compression, the relation between temperature and the pressure, T2 by T1 is equal to P2 by P1 gamma minus 1 by gamma. So here P2 by T1 is a compression ratio and it is called RP. So this RP gamma minus 1 by gamma. So now this T2 is equal to T1 RP to the power gamma minus 1 by gamma. We got the first equation, the relation between T2 and the T1 in context of the compression ratio. Now if you see the process 2 and 3, this 2 and 3 is a isobaric process where T2 is equal to P3. But if you see this TS diagram, temperature is falling down. It means T2 is greater than T3. So we have to write T2 minus T3, not the T3 by minus T2 as we have done in the previous, in our Brayton cycle. So here process 2 and 3, here the heat is rejected at a isobaric heat rejection. It is called the QR. So QR is equal to MCP T2 minus T3. Now if you take the process 3-4, that is the isentropic expansion process. So work is produced by the turbine. So here 3 to 4, here expansion is taking place, volume is increased, pressure is decreased and temperature is also decreased. And this reduction in temperature is very high. So here we can see that T3 by T4 is equal to P3 by P4 gamma minus 1 by gamma. So this T3 is equal to T4 P3 RP to the power gamma minus 1 by gamma. So here we got equation 1, equation 2 and now we will go for next. So how much net heat extraction is Q net is equal to heat rejected minus heat absorbed. So heat rejected is MCP T2 minus T3 and heat absorbed is minus MCP T1 minus T4. According to the first law of thermodynamics, for cyclic process, net heat interaction is equal to the net work done, means del Q is equal to del W. So W net is equal to Q net is equal to MCP T2 minus T3 minus MCP T1 minus T4. Now to find the coefficient of the performance. So here we can find out the work done or work required or heat. It is a difference in heat supplied. So now coefficient of performance is called the COP. Here we don't say the efficiency. In engine, we always say the efficiency because we will get always less than what we supply. But here it is not so. We are supplying some amount of work, but we are able to get more refrigeration effect. So the coefficient of the performance will always be more than 1. So that is the difference between the efficiency and the coefficient of performance. So now coefficient of performance is heat absorbed, means in 4 and 1. In the process 4-1, heat is absorbed and net work done, which we have just now find out, MCP T1 minus T4, and net work done is equal to MCP T2 minus T3 minus MCP T1 minus T4. So here we will take out MCP, MCP, MCP. So here we will get T1 minus T4 divided by T2 minus T3 minus T1 minus T4. So now we have already find out the T2 and we have already find out the T3. So here T2 is equal to T1 Rp to the power gamma minus 1 by gamma minus T4 Rp to the power gamma minus 1 by gamma minus T1 minus T4. So here if you see, if I take this T1 and this T1, so what I will get here? Here I will get Rp to the power gamma minus 1 and T1 minus T4, T1 minus T4 will cancel here. So here you can see here T1 minus T4 is equal to, if I take the T1 minus T4 common, so here I will get Rp to the power gamma minus 1 and minus 1. So this is cancelled. So you will get the coefficient of the performance is equal to 1 by Rp gamma minus 1 by gamma and minus 1. So it is raised to the power Rp raised to the power gamma minus 1 gamma minus 1. So this is the equation for the coefficient of the performance of the Bell Coleman cycle. This cycle is used for refrigeration and air conditioning purpose. So hope you have understood this derivation of coefficient of the performance of this Bell Coleman cycle, and now we will be trying to solve one problem. By this problem, we will be able to understand the application of this problem. So numerical 1 on Bell Coleman cycle. A dense air refrigerator operates on Bell Coleman cycle and is required to produce 12 tons of refrigeration. The cooler pressure is 4.5 bar and the refrigeration pressure is 1.5 bar. The air is cooled in the cooler to a temperature of 52 degrees centigrade and the temperature of air at inlet of the compressor is minus 10 degrees centigrade. Determine for the ideal cycle COP of the system, mass of the air circulated per minute, net power per ton of refrigeration. So this is the thing. So first if I draw PV diagram or TS diagram, okay, whatever may be. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. 1, 2, 3 and 4. This is the compression. This is the expansion. This is the cooling. This is the absorption. Okay, so a dense air refrigerator operates on Bell Coleman cycle. So the cycle is Bell Coleman cycle. This cycle is used for the refrigeration system. So arrow will be in anti-clockwise direction. That also you have to required to produce 12 tons of refrigeration. So QR is equal to 12 tons. The cooler pressure is 4.5 bar. So P2 is equal to P3 is equal to 4.5 bar. And the refrigeration pressure, that is P1 is equal to P4 is equal to 1.5 bar. The air is cooled to a temperature of 52 degrees centigrade and the temperature of the inlet. So here temperature T1 is equal to minus 10 degrees centigrade, and the air is cooled in a cooler. So in the cooler, how much? Means T3 is equal to 52 degrees centigrade. So these are the things. So we have to find out the COP, we have to find out the mass of air circulated per minute and net power per ton of refrigeration. These three things we have to find out. Let's see how we can do and we can go ahead. So here solution is like this. Refrigerating effect is given 12 ton. P1 is equal to 1.5 bar. T1 is equal to minus 10 degrees centigrade plus 273. We will get 263 Kelvin. P2 is equal to 4.5 bar. T3 is equal to 52 degrees centigrade plus 273. We will get 325 Kelvin. What we have to find out? We have to find out the mass of the air. Then we have to find out the power per ton of refrigeration and coefficient of the performance of this system. So we can see this TS diagram of this. So 1 and 2 is a compression, 2 and 3 is a cooling, this is the expansion, and this is the absorption. So these all things are mentioned here. So first we have to find out the various temperatures, because 1, 2, 3, 4 all the temperatures are required to calculate, but all are not given. Only T1 and T3 two temperatures are given. Means this one T3 is given and T1 is given. These are given. Pressures are also P1 and P2 is given. So we can find out the P2 by P1. So P2 by P1 is equal to 4.5 by 1.5. We will get 3. So RP is equal to 3. So process 1-2 is isentropic compression. Here T2 by T1 is equal to P2 by P1, gamma minus 1 by gamma. So T2 is equal to T1, RP to the power gamma minus 1 by gamma. T1 is equal to 263, RP is equal to 3 here, and 1.4 minus 1 by 1.4. Here T2 is greater than T1. So we get here T2 is equal to 360 Kelvin. So we got here 360 Kelvin. So this we have to check that it should be greater than that T1. Then only compression will take place. Otherwise there is some problem in your calculation. Now we have to see the process 3-4. It is an isentropic expansion process. And the ratio T3 by T4 is equal to P3 by P4, gamma minus 1 by gamma. So T4 is equal to T3 divided by P3 by P4, gamma minus 1 by gamma. P3 is equal to P2 and P4 is equal to P1, and P2 by P1 is equal to RP, and RP is equal to 3. T3 is given 325. 325 divided by 3 to the power 1.4 minus 1 by 1.4. We will get 237.45 Kelvin. So we got the T4 237.45 Kelvin. So now we have to find out the COP of the system. Coefficient of the performance is a refrigerating effect by power. So refrigerating effect RE by power, and we know the RE is equal to CP T1 minus T4. So 1.005, 263 minus 237, this one 0.45. So we got the refrigerating effect is 25.676 kilojoule per kg. This we got the refrigerating effect. Now how much is the power that we have to? So refrigerating effect we got it now. So now power is equal to power supplied to the compressor minus power given by the turbine. So we know that power is equal to Cp T2 minus T1 by the for the compressor, and we got the power from the turbine which is given to the compressor is Cp T3 minus T4. So here 1.005, 360 minus 263 minus 325 minus 237, it is T4, T3, T1, and this is the T2. So this putting the value, we got the power P is equal to 9.497 kilojoule per kg. So we got the power now. So from here we can find out the, I think we have, so here we can see here that efficiency COP is equal to refrigerating effect 25.676 divided by power is 9.497. 9.497. So just roughly you will get nearly 2.7. COP you will get 2.7. It is not mentioned here. Next we have to find out the mass of air circulated per minute. So here RE is given 12 ton. So refrigerating effect is equal to MA Cp T1 minus T4. So 12 ton. So 1 ton is equal to 3.517 kilowatt. This you have to remember, please, because refrigerating effect is always given in tons of this thing, and 1 ton is equal to 3.517. So if you multiply by 12, you will get 42.2 kilowatt. So 42.2 kilowatt is equal to MA, Cp is equal to 1.005, T1 is equal to 263 minus 237.45. So mass of the air is equal to, we will get here mass of air is equal to 42.2 divided by 1.005, 263 minus 237.45. So you will get the answer here 98.61 kilo kg per minute. And here we will get here second. So in the second, if you multiply by 60, you will get multiplied by 60. So you will get 98.61 kg per minute. So this we have done it. Now we will find out the net power per ton of refrigeration. Net power per ton of refrigeration. We have find out this power, but it was not per ton. So now COP, we know that RE by P. COP we have find out 2.7 and RE is equal to 3.517. It is for 1 ton of refrigeration. 3.57 divided by P. So P is equal to 3.517 divided by 2.7. It is 1.303 kilowatt. So power required here, power required per ton of refrigeration is equal to 1.303 kilowatt. Okay, so this much power is required for 1 ton of refrigeration. So that is we have got all the 3 answers. In the next class, I will be starting the next module number 5, and that module is a heat transfer, and in that we will be learning about methods of heat transfer, conduction, convection, and the radiation. We will be also studying about the Newton's law of cooling, Kirchhoff's law for the radiation, also flux, heat transfer rate, flux. Also we will be studying about the compressors, different types of compressors used for the different mechanical systems. This all we are going to study in our next module. The references for this lecture was from the P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's, Yunus, Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. These are my favorite books. I always refer Sengel for my all the topics. Any questions, you are welcome to ask me. My email is yddwivedi@gmail.com. This is my email. You are always welcome to ask the question. If you like this video, please like and subscribe. Also give comment if you want anything to ask. Thank you very much for the joining. We will see for the next module, heat transfer, in my next class. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.